Wow, this is really amazing to be here. What is it, 16 days after the reveal of some of the first images from the James Webb Space Telescope. 27 years in the making. So we're going to get to the big reveal. We're going to get to the science. I want to begin with where this all really started. And John, you joined this project in, what was it, 1995?
I joined it in 1995, and there was already a dream that people had written a book that we needed to build this telescope. And would I like to work on it? Sure would. It's the coolest thing that I'd ever heard of. Now, and I'd already done a measurement of the Big Bang.
Right, exactly. So you had already done a measurement of the Big Bang. That's insane. So the project that you were known for, which you eventually were co-recipient for the Nobel Prize for, was COBE, Cosmic Background Explorer. Can you tell us a little bit about COBE and what COBE did?
Yeah, we measured the Big Bang, which means we measured the heat of the Big Bang itself. It fills the universe completely now. Any direction you look, that's where it is. And we measured the temperature, we measured the color, which is colorless, meaning it fits a formula. And we measured hot and cold spots. And those hot and cold spots tell us that that's why we're here. Mm-hmm. If there were no hot and cold spots in the Big Bang, then gravity would have not stopped the expansion of material and turned it around to form galaxies and stars and planets and people. So we're here because of those spots. And so that's pretty cool.
So to some extent, you were looking at something before there was anything else. There were no structures. Nothing was there but this primordial soup. It's, 380,000 years after the Big Bang. So that's even earlier than James Webb Space Telescope is going to look.
Yeah, you can't see any farther back than that.
Mm-hmm.
And the Webb telescope was designed to look for the first things that grew after that.
Mm-hmm.
What was that first thing that grew? Stars, galaxies, black holes? Nobody knows yet. So we're about to find out.
Here you've done this Nobel-worthy work, even if you didn't know you were going to get the Nobel Prize, and you could have put your feet up like the rest of us and watched Netflix, all the time. What possesses you to take on such a high-risk project? Because it was high risk from the beginning.
Well, it's high risk only if you think it's not worth doing. But it was worth doing from the very first moment. Mm-hmm. So we just have to do this. Yeah. If you want to know the answer, this is what you have to do.
Yeah. So we'll motivate why Hubble predated that and gave that motivation. And Wendy, by the way, I was at the announcement of the COBE data. I was a student, and I remember it so well, and that must have been the first time that I met you, John. And I remember the first time, Wendy, when I met you, you were in the middle of this huge controversy. Can you tell us a little bit about this controversy?
Well, that would have been likely in the late 80s, early 90s.
Yeah.
And at that time, astronomers were arguing about the age and the size of the universe, the expansion rate of the universe at a level of a factor of 2. And we didn't know whether the universe was 10 billion years old or 20 billion years old.
And how old do we think it is now?
13.7 or 13.8.
Yeah, and that's pretty solid.
That's now very solid.
So back then we didn't know. 10, 20, somewhere in there. And now it's pretty solidly 13.8 and 13.7.
Yeah, and that was a pretty unhappy situation because we couldn't learn about masses of galaxies, luminosities of galaxies. Everything had to have a little h beside it to allow for this uncertainty.
So basically you were measuring the expansion rate of the universe since the Big Bang, and it was hard to ascertain.
Yeah, it turned out to be a lot harder to measure than Edwin Hubble originally thought it would be.
You're a very young scientist, and you enter this debate, and I had so much anxiety watching you, I have to tell you. There were these powerhouses, like Alan Sandage, and these powerhouses who had very strong opinions, and you would kind of calmly get up and give your lecture, and you would hold to your measurement, which was not what they wanted to hear.
No, but I always felt that you have to be led by the data, and I was very fortunate to come along at a time when the Hubble Space Telescope was launched, And prior to that, the CCDs, charge coupled devices, had been developed. And so new technology really helped to propel this field and to allow us to solve it. So I stuck close to the data, and you're right, they were strong personalities, and they did kind of nasty things sometimes.
Yeah,
to a
I
junior
saw some
scientist.
nasty things happen. I was so impressed always, Wendy, just while I have you in front of 1,000 of my closest friends.
Nice to meet you.
How much I admired you for your cool in the way that you handled it. It was very inspirational. Let's talk about Hubble, though. Here's a Hubble Space Telescope, which is a lot of the precursor to James Webb. John, it's not going to win a beauty contest compared to the James Webb, is it?
Well, I think it's beautiful. And it's like, don't you like your dad? It's beautiful in its own special way. It's a beautiful
It
tube.
is beautiful.
It protects the telescope from all kinds of things. And the Webb telescope is out there unprotected. So
Right. So the Hubble Space Telescope looks like this because it's protected. And that's really interesting. And as you say, we'll talk about the instrumentation of James Webb, but it is completely, essentially exposed. Tell me a little bit about Edwin Hubble himself, the American astronomer after whom the satellite is named.
Oh, well, he was a pretty famous guy. Do you know more about him than I do, probably?
Maybe.
I know he faked a British accent sometimes.
Yeah, he went off to Oxford. He
came
was
back
a Rhodes
with
scholar, and and came back with an accent. So he was at the Carnegie Observatories, where I spent many years of my career. And when he arrived at the Carnegie Observatories, there was a debate at that time about the nature of objects that were called nebulae. Nebula is a Greek word meaning fuzzy. And there was a question about whether these nebulae were regions in our own Milky Way galaxy that were forming new stars, or whether they could be galaxies, although that word didn't exist at the time, but systems like our Milky Way at much greater distances. And Hubble was the person who was able to show that they were at much greater distances.
So this is the 1920s, and he's at Mount Palomar Observatory in this picture. And in the 1920s... Mount Wilson, sorry. And we knew that we lived in a galaxy, the Milky Way, which is a collection of 300 or so billion stars. But we did not know if ours was the only galaxy. And that's 100 years prior to now. We did not know that. And I want you to tell us a little bit about this group of women. I'm just going to mention, these were female astronomers at the turn of the previous century. They were referred to as Pickering's harem, because Charles Pickering, then director of the Harvard Observatory, fired all of the male astronomers and only hired women, and they were called Pickering's harem. But I want you to speak specifically about Henrietta Levitt in this picture. She's very relevant to your work, too.
Henrietta Levitt was the astronomer who discovered that there was a certain type of star called a Cepheid star. It had been known since the 1700s in stars in our galaxy that varied in their brightness over time. And she was able to show that the rate at which they varied was related to how bright the star was. And that had the implication that if you could determine how bright a star in our own galaxy was, then you could measure the distances to more distant objects by using the inverse square law of light. So she was interesting. She was deaf.
So she's the one sitting at the desk by the poster? Is that Henrietta Levitt?
Can't
Sitting
see her.
at the desk by the poster? Is that her? I think that's her.
I think that is her. I think you're right.
I don't know. I wouldn't swear to it.
She was deaf, and she never got to see the implications of her own results. She died in 1921, and Hubble made his first measurements in 1923, and he discovered the expansion in 1929. So she never knew the implications of her results. But everything we do today, especially with Hubble, using Cepheid variables, depends on her discovery.
So this is one of the images that Hubble, the person, not the satellite, took, and it says October 6th, 1923 on it. Can you explain to us why this is such an iconic image, why it's so important?
Yeah, he must have been taking these images around now, 100 years ago, because he discovered the variable. You can see he's marked VAR with an exclamation mark, and there was an N that he crossed out. So he first thought it might be an object called a nova that also changes in brightness, but he had the realization that this was, in fact, a Cepheid variable, and that then he could measure the distance to the object. So this is Andromeda. Probably many of you have seen this. If you're in a dark sky, it's actually observable with the naked eye, but it's the closest spiral galaxy to our own. And it was one of the first galaxies that he discovered the Cepheids in. And this is a glass photographic plate. That's what the detector of the time was. In fact, until the 1980s, it's what astronomers used. And there's actually an interesting story that Harlow Shapley, who was the person who discovered that the sun is not at the center of our Milky Way galaxy, he was also at the Carnegie Observatories, the Mount Wilson Observatories at the time. And the mule driver who brought up the equipment to build the 60-inch telescope before there were any roads up the mountain, he eventually got hired. He worked with Hubble. They published papers together. And he marked on the back of one of these photographic plates where he thought the Cepheid variables were. But Shapley was convinced that the Milky Way was all there was. He had measured a large Milky Way, and he took his handkerchief and removed the marks and told them never to do it again, and he missed the opportunity to discover external galaxies.
So this is really the first time, using Henrietta Levitt's work, Hubble and anybody had realized that there was another galaxy out there. Now, Hubble, the satellite, takes this image of Andromeda. John, can you just tell us a little bit about Andromeda? Why it's significant to us?
Well, it's especially interesting because it's so close by, and we can see it so well, and it's only, 3 million light years away, something like that. So you can make out individual stars all over it now with the big telescope that we didn't have back then. Now that we have a telescope in space, the images are so much sharper, and so we mapped the whole thing. And you can see it's got a couple of bright satellite galaxies too. We do. The Magellanic Clouds in the southern sky are like that in a way. And both cases, they're orbiting around and they're about to fall in. So that's part of our story of galaxies. The galaxies appear to be made out of little bits that have been falling together, pulled together by gravity over billions of years. So we're seeing it right there in front of us. And that's part of the story we want to understand. And it's spiral, and so is ours.
Yeah. So we go from thinking maybe we're the only galaxy in the universe to realizing there's a nearby galaxy, Andromeda. And then Hubble, the satellite, begins to see that the universe is replete with galaxies. And what would you estimate in the observable universe would be the count of galaxies?
We used to say 100 billion galaxies, each with 100 billion stars, and now it's more. A lot more.
At some point, it's just a lot.
Yeah.
Now, how does JWST, James Webb Space Telescope, look at galaxies differently from the Hubble?
Well, we can pick up infrared light. So infrared light's like regular light, but longer wavelength. So why do you care? Well, it comes from objects that are cooler, that are not warm enough to emit visible light, or that are hidden inside dust clouds, because the infrared light can go around a dust grain. When you go down to the airport and they scan you through your clothes, they're using longer wavelengths to see through the cloth. So that's one thing. And, so you can even hope to see stars at the most distant universe, galaxies, because the expanding universe stretches out the light, the wavelengths of light as the light is traveling. So in order to see those first galaxies, we need an infrared telescope to pick up the light that started off as ultraviolet. Mm-hmm. So that's the sort of the original motivation, the biggest motivation, the hardest motivation that said build us this telescope and not only make it do infrared, make it huge.
Right, make it huge. So we're going to talk about that. And while we show this time-lapse photography in the background of different phases of working on the instrument, tell me how big it is.
It is about 21 feet across the mirror. And you see in this image here, there's a golden hexagon, 21 feet across. It's made out of 18 smaller hexagons.
So that's like the size of a house.
It's
as big as a house.
It's bigger than
Small
bigger
house.
this stage.
A New York City house.
Yes. And then it has to be protected from the sunshine because it's got to get cold. So the umbrella is called a sunshade. It's as big as a tennis court. Mm-hmm. So imagine your favorite tennis star running back and forth. Ours is bigger.
So the mirrors themselves, which we're seeing here, are made of what?
They're made of beryllium, but they're coated with gold.
So they're really gold.
Yeah, it's real gold, which is because it's the best reflector for infrared light. But the beryllium has its own story to tell, because where did it come from? It came from the very earliest universe. There's very little of it left. So beryllium's a scarce material, but it's ultra light, ultra stiff. So it was the material that we needed to have to make this incredible thing.
And the mirrors are very, very smooth.
Oh yeah, it is. If you were to make the mirror as big as the whole continental United States, the ripples would be about that big.
Right. So this is already a stunning kind of engineering achievement. I hear there's a dark art to polishing mirrors.
Yeah.
So you have to make the instrument big. Why do you have to make it so big?
Well, big because two things. One is the things you're looking for are faint, so you need to collect a lot of light. And number two is light's a wave, as it appears to us, so it bends around corners. It's called diffraction. So if you don't have a big telescope, you get a fuzzy image.
And does something the size of this stage, the size of so this is folded, this is not completely open in this image yet. When it's completely open, does that fit in a rocket?
No, it doesn't fit. So it's definitely a lot bigger than the rocket. The rocket's smaller than this stage, at least the volume you can use. So it's folded up like a butterfly into its chrysalis.
Now, let's be clear, this is the most complex telescope ever designed, and that is one aspect of it that is quite terrifying, is unfolding in space. That's never been done before.
Yes, if you're an engineer, you say, well, that's a wonderful problem to solve. If you're the budget guy, you say, how much is that going to cost us? And if you're the astronomer, say, please let it work.
Now, Wendy, you were on the committee when there was a lot of back and forth, and some very notable astronomers had gotten together and basically said, forget it, just make it smaller, make it fit in the telescope. And you didn't agree with this. Do you remember your thinking at the time?
So this was a committee that was charged to think about what would come after Hubble. And we knew to have the science that John's been talking about, you would need a bigger telescope. And so but as a committee, in the first part of this discussion, the telescope was actually much smaller. It was a 4-meter telescope, not a 6.5-meter telescope. But there were those of us who felt that in order to achieve the science and to go to all that effort, which we heard about, to make this work, you really wanted to have a powerful telescope to take that next leap after Hubble.
Now, I heard a rumor that one of the NASA directors at the time essentially said, you're all a bunch of scaredy cats. If you don't make it bigger, there's no point in doing this, and that the committee erupted in applause.
That was an American Astronomical Society meeting. It was Dan Golden at the time, and yeah, he said, you're a bunch of scaredy cats, you should think bigger. And he set a budget that was very low, very low.
There's 600 million or something?
500.
500 million?
Yeah. And not surprisingly, there were 3 bids that came in around 498, 499, 498, and they all said they could do it.
Right.
But it was a challenging project.
John, do you want to admit what the final price tag was?
Well, I think nobody actually believed that was the real number when we told him. Because it was less than the Spitzer Space Telescope, which was already costing more than that and was only 85 centimeters across. So clearly that was a wrong story. Everybody could tell. But the boss said try, so we'll try.
Well, at that time the phrase was faster, cheaper, better, and I remember astronomers saying, pick 2 out of 3.
Yeah, and everybody knew that.
Yeah.
But we said, it's still worth trying.
Yeah.
We got to figure this out. We got to find a way, because there's no other way to get that science.
Now, we see, oh, sorry, John, I didn't mean to interrupt you.
That's all right.
We see in this image here the shields you were talking about. Now, those are phenomenally thin. Can you give us a sense of how thin?
They are about 0.02 of an inch thick. So it's about the thickness of the plastic laundry bag you have when you get your laundry bag.
And if they snagged, unfurling in space, because they also have to be folded up to fit into the rocket.
Yeah, folded up very carefully as a kind of accordion pleated to fit in there. So if they snag, you could get 2 things. One is maybe they might not come out all the way. That would be really bad. Or they might tear. So how do you prevent that? Well, you practice, you rehearse, you make it do it, and then of course it doesn't work right the first time. So you watch what you did wrong and you fix that. You do it again.
Yeah.
And you do it again until it works. And that's
I mean,
the only way you can possibly do this.
I snagged my dress getting it out of the closet today. If that had snagged and that was not working, that's kind of would have been the end of the telescope. I mean, I think people need to understand how every step was so delicate. Now, the way, when the telescope unfolds and it fits together, I've heard that it fits together at a distance less than a virus. Does that sound about right to you? It's very snug.
It's very, well, the hexagons are not next to each other. They're not that snug to each other, but they have to be adjusted very precisely to a tiny fraction of a wavelength of light. So that's a measure of perfection, and it came out to be about twice as good as we promised, which is really spectacular. Of course, why did we do that? Because you don't know in advance. If you don't have a little bit of margin between the promise and the thing you're doing, it might not come out. So got to be a little better.
You joined this project in 1995, and by the time you're taking this instrument that's now 14 years overdue, and we'll discuss why when we discuss the Hubble, because there was probably some lessons there, and it was 20 times over budget. And so now you have this stunning, unbelievable achievement, no question, incredible engineering achievement, and you stick it on some explosives and you launch it into space.
Yes, it's kind of scary, but I was not scared. I just thought, this is what we do. We do everything you can possibly do to make it right, and then you find out if you did.
Do you think you took
That's why it's amazing that people like John actually were responsible for building this telescope, because I don't think any astronomer was as calm as you were.
What I was going to ask you.
It was scary.
Well,
when you think of all the things that could go wrong. And
Watching the
that's it.
launch itself.
This thing was out 1,000,000 miles away. There are no astronauts the way that Hubble could be repaired.
Of course, the reason I could be calm was that I know the engineers that I worked with, and I knew what they were doing. So they had 7,000 requirements to check. And they had something like 600 or 700 risks that we analyzed to say, make that not happen.
Right.
So they had a good system. So you couldn't do it without it either.
There was this incident, which I wanted to ask you about, just as one of the many, many examples of things that could go wrong. Here's the primary mirror coming out of a cryogenic tank where you were testing it. Now, the mirror has to be very, very cold. And it has to be kept cold because it's going to be cold in space, and that's part of the shield, is to protect it from sunlight and protect it from the heat of the instrument itself. What went wrong here with this test? Wasn't that during Hurricane Harvey?
Well, it wasn't a problem with the telescope, but we did have a lot of rain. 50 inches of rain on the outside of the building. And our precious telescope was inside the vacuum tank. And here's the picture you can see on the screen of the telescope, and that's the door of the vacuum tank. So it went in, it was perfectly protected inside the tank, but the people that were working on it, they were not protected. They had to go back and forth to work and deal with 50 inches of rain.
And there was liquid nitrogen required to keep it cool. And the story I heard was that you had to ask for liquid nitrogen to be delivered in the flooded streets during a hurricane as a matter of national importance.
That's true. We did have to do that. If we hadn't got the nitrogen, then we could have damaged the telescope.
It's all just to speak to how delicate this experiment is, and then you put it on this explosive rocket and you send it where? People keep hearing things about L2. Where does it go once you put it on?
It's 1,000,000 miles from Earth. It's the opposite direction from the sun, so it's overhead at midnight. So, I don't know, it's up there right now, more or less. So, 1,000,000 miles out. We put it there because we can keep it there. It doesn't get any farther away from the Earth as we orbit around the sun. It moves around the sun with us. So it stays 1,000,000 miles away the whole time.
That is how many times further than the moon?
4 times.
4 times further away than the moon.
So we've never sent a person out there that far.
Right.
So which means we're not fixing it.
Right. So when it deploys, it has to deploy perfectly, first time, that's it, flawlessly.
Yeah.
Yeah.
So we did.
Yeah.
We had backup plans for everything, but we didn't have to use any of the backup plans.
Amazing. I want to go back to Hubble because I think one of the reasons, and maybe I'm projecting, JWST was 14 years overdue and over budget was because you were so careful. And you were being careful because the Hubble, which is only 340 miles up, so it's just right here, right? In comparison, was a disaster. Wendy, would you say it was a fiasco initially, Hubble? People don't remember this.
It was tragic. It was really sad. Here was a telescope we'd all been waiting for, and when the first images were taken, it was out of focus, and it hadn't been
This
tested.
is one of the first images that was taken.
Yeah, this is M100, in fact, in the Virgo cluster. That was one of the first objects that we looked at when we started the Hubble Key project. And we had to wait until astronauts could go up with repairing optics to allow the telescope to focus. So it was a really depressing time for the astronomy community.
So we actually sent astronauts up. I mean, it's a very risky business sending astronauts into space to do the repairs, basically, to fix Hubble. So there were some arguments just to leave it as space junk, just to give up on it.
Yeah.
How did that get past? People just throwing their arms up and saying, forget it, it's over, it's junk.
I think the fact that there was a really good idea of how to fix the optics, and I think the fact that everybody could watch what happened. This spacewalk as the piano-sized camera was taken out, the wide-field planetary camera, and new optics were installed.
It was a couple years later? How long was it later?
So the launch was in 1990, and then the repair was in 1993, December.
So 3 years.
Yeah.
Do you remember being extremely disappointed, John?
No, I wasn't paying any attention at all. I was still working on the Kobe satellite.
You were
I
laughing.
just thought, they better get this right. But
Did you
But I
ever-
think it made people, interested in the Hubble results after that,
Right.
because there was a human story to it too. Astronauts who went out and did this repair,
Yeah.
and then it worked spectacularly.
Here's an image.
better than originally
Better than originally
originally
designed.
planned, because the repair optics could actually correct imperfections that and made it a more.
So this other image is what we're used to seeing when we see Hubble. John, did you ever have any disasters earlier in your career?
well, sure, of course, doesn't everybody? My thesis project did not work. Nevertheless, the idea of
hired
it was
him
a
anyway.
good one.
What was that? What was that?
They hired him anyway.
Yeah.
Yeah,
He
and
did
so-
okay in the
yeah.
end. Yeah.
Was it a
So-
balloon project?
It was
Is
a
that-
balloon payload. It was to measure the Big Bang radiation, and it went up and it did not function. So, okay, well, it
Lesson
did
learned.
good enough work to write a thesis, but that's pretty disappointing.
Mm-hmm.
So, tried to become a radio astronomer, and I came here to New York City at the Goddard Institute for Space Studies up on 112th and Broadway.
Mm-hmm. Yeah.
And that's where I was when NASA said, "Anybody want to propose a new satellite?" And I said, "Hey, my thesis project failed. We should try it in outer space."
Fail upward.
Yeah, so it did work when real engineers made it work.
Yeah. And again, Kobe was that remarkable satellite. When the results were first revealed, the audience erupted into spontaneous applause.
It was a standing ovation.
Yeah.
It was,
Yeah,
it
I
was
put my
really
little graph up, and
Yeah.
there it was, just a little curve. Anyway,
just a little curve. Yeah.
just what it was
basically-
supposed to be.
Yeah. So it was
Except
a
maybe it wasn't.
theoretical prediction, and then you put the data on top of the theoretical prediction.
And then you couldn't even see the data points. You had to magnify them by about a factor of
was just
1,000.
like
No,
boom,
that
boom,
was,
boom, boom,
later,
boom.
but
That was
the
later,
first
yes.
first day we didn't even know the right size of the error bars. But
Yeah.
anyway, we knew they were small.
Yeah. Quite an achievement. I mean, you basically saw the oldest thing anyone's ever seen.
That's right.
Let's talk about what happens after deployment. I want to run, this is a NASA animation, a simulation of how it was supposed to go after it was out in space. And you can see the days and the hours counting above, and it's telling you the orbit below. Can you talk us a little bit through what's going on here?
Yeah, sure. So first you blast off from the Earth, and it's just a commercial rocket. The Europeans build it. It's called the Ariane 5. And they launch it straight out towards the moon, or actually past the moon. You don't want to go close to the moon. And so the first thing that happens is you unfold the solar array. You need electrical power. Next thing, pretty soon after that, unfold the antenna that points back at Earth so you can talk as fast as you want. And then gradually you unfold everything else. First, you unfold the sunshade, and then you let it sit there for a while and make sure it's all right. It happens in many steps, and it would take altogether 2 weeks to see this thing that you're seeing in the movie in about a minute. 2 weeks. And it's all done by step command from Earth. And the robot is not doing it all alone. We're watching it and saying, yeah, that's okay. Okay to go do the next step.
I watched a lot of it. It was weirdly mesmerizing.
Yeah.
Weirdly mesmerizing. It would be like very obscure commands. Command number 325 being executed. And then he would say, like, copy. I mean, I'm obviously not accurately representing it, but it was mesmerizing to watch it.
Yes.
Actually.
And of course, nobody actually could see that. This is all animation.
It's all animation, right. And Wendy, were you watching over the couple of weeks?
Oh, yeah. And I was biting my nails. The number of single point failures was daunting.
Right.
And
Can you tell us what a single point of failure is, Wendy? What that means?
Well, simply that if that single thing didn't work, the telescope would be a failure.
Right. And there were hundreds.
There were hundreds. Most of them are the devices that protect that giant sunshade and keep it from shaking itself to death during the launch. So here you got this giant piece of folded plastic. What's it going to do? Flap around. Better not do that. So you stick it down, but then you have to let it go.
Yeah. And it was obviously thrilling that it deployed flawlessly the first time as it needed to. It got to that crazy orbit it's on. That's 1 million miles away. And it started working, but it was hit by meteorites.
Yeah, we expected it. Those lovely things you call a meteor shower, well, we don't like those because they're little sand grains flying through space at 20, 30 kilometers a second. And if one would hit your foot, you would hurt. It would hurt. But if you had it in your fingers, you wouldn't even be able to tell you had it because it's so tiny. So what happens is they make a little pit in the mirror when they hit. And we don't like that. But we planned for it, and we can adjust the mirror to compensate afterwards because all those 18 hexagons are on motors, so you can adjust them. So we've got more or less one a month, little tiny ones, and one bigger one. So we're just the little tiny ones, we honestly don't care. It's all okay. But if we get a lot more big ones, we would care.
And it could just be a fluke.
It could be a very rare one that never happens again, or it could be another one coming. You just don't know.
I want to go back to the Hubble again just for a second as motivation for the James Webb Space Telescope. And Wendy, you worked with the Hubble a lot. You used that data. It wasn't just, Cepheid variables are very interesting. Can you tell us a little bit how your own work was related to the Hubble instrument, how you used it?
Yeah, so I mentioned the debate at the beginning, this factor of 2 uncertainty, and every new facility has an umbrella-like program that says this is what the telescope will do, even though it will probably do hundreds of different kinds of scientific projects. But settling this debate was what the Hubble Space Telescope was built to do. And so there was a question before the telescope was launched of what could Hubble do that no other telescope on Earth could do? And if Hubble were to fail, what wouldn't get done? And solving that debate was resolving that.
Why is this issue over how fast the universe is expanding from the Big Bang? So basically, we think there's this initial moment, there's a Big Bang, the universe comes out expanding. Why is that such a crucial debate? Why isn't it just, it's a number, we've got it right, we don't have it right, but we know it's expanding, that's the important part. Why was it so crucial?
Yeah, essentially it's the most important cosmological parameter. So understanding how the universe is evolving depends on knowing an accurate value of the Hubble constant. If you know that value, you can also learn other things about the nature of the universe. And for example, the amount of dark matter in the universe, the amount of dark energy in the universe, and specifically, if you can measure distances really accurately, then you can determine the properties of objects like luminous galaxies and stars and every object you want to measure.
It's the age of the universe in part because we can't tell the age of the universe because we're kind of running the movie backwards, and it kind of matters how fast the movie's running to decide how long ago it started. So that's one thing. But also, as you're saying, there's this dark matter, dark energy problem. John, did you have something I sense you want to contribute?
one of the curious things is we started off not knowing that the universe would be accelerating now. When I was a graduate student, we knew that it was logically possible, but said nature wouldn't do that.
So
We
the
know that
universe
nature
isn't
would
just
not do that.
expanding, the expansion's getting faster.
Yeah,
Well,
expansion is
in
getting
fact,
faster.
So when we saw the image of M100, so when we first got our first observations from
Whistling
Hubble,
back here?
yeah, we measured the expansion rate, and it essentially suggested that the universe was younger than the oldest stars in it. That is, the universe had not been expanding long enough to have a universe
So
where you
that's
could
a
have
real
stars.
paradox.
A huge paradox.
Right.
And that eventually got resolved with the discovery of dark energy, by and large. It was, the universe has been speeding up in the intervening time, and so it wasn't always expanding this fast.
Can you tell us what dark energy is, John? What that means?
Of course not. No, we've observed that distant galaxies are too faint. It is right about 20% too faint. So the explanation is the acceleration, but we do not have a story in physics that says it should be like that. There's no big fundamental quantum mechanics prediction. It's just this is what the universe does. So okay, we better accept it.
So we just call it dark energy.
We call it dark energy.
But we don't know what it
because
is.
It's a cool name, but it's actually misleading because we don't know if it's energy and it's not dark. It's transparent.
It's invisible.
It's invisible.
Right. It's definitely not dark. It's probably here right now.
Yeah. So
And
there's
it's
some
just
of it
invisible.
here in my coffee cup. But
Yeah, you have some in your coffee cup. So Wendy, basically Hubble realizes there's another galaxy nearby. Suddenly galaxies aren't alone. Then the Hubble satellite begins to detect all kinds of galaxies like this. People like you use those to realize not only are there other galaxies, but the universe is huge and it's expanding. Would that be a fair story?
That would be fair. And I think, you know, the beauty of telescopes like this is that we can actually learn something about the universe that we live in. It's and we do that by studying the properties of light. That's what we get.
Now you know what this is a setup for. This was the Hubble Deep Field, which looked at a tiny piece of the sky. This is just to show you. Imagine staring into a very small piece of the sky relative to the moon. That's about the size of the square relative to the moon. And when the director of the Space Telescope Science, I'm getting it all wrong because I'm getting tired, the Institute was using his director's discretionary time to stare into a dark area of space for maybe 10 days. People weren't happy about that.
No, and he had, in fact, an advisory committee that really gave him a lot of grief over that. They didn't think it was a good idea.
Now, why did they not think that was a good idea?
They didn't think there would maybe be very much to learn, and there had already been observations taken, and not much had been learned at that point. But he felt very strongly that going deeper than anyone had ever gone before we'd learn something new, and he was right.
What did you think about that decision, John? Were you aware of it at the time?
Well, I wasn't paying much attention, but it clearly turned out to be beautiful because the minute the pictures came out, everybody said, "Oh my gosh, look at that!"
Yeah, this is what
not
came
what
out.
this is not the story we told you.
Yeah. Can you tell me?
People were quite sure that galaxies formed very recently, and that was very famous theorists were sure of this. So we knew what telescope to build to find that, and then they took the picture, and it wasn't like that at all. And then, moreover, they looked at the picture and they said, even the Hubble cannot see the first galaxies growing. You could tell right away we need another telescope that's bigger and more powerful and can pick up infrared. So what we see in the picture are nearby galaxies that have shapes, and there's a few little red specks in there. And those are the ones that are the most distant. You can't even see that they have a shape, but we know from the color that they're the most distant. And so, okay, those are the ones we would identify as the first galaxies, but the way we interpret the picture is they're still not the first ones. So please build us another telescope.
Every object in this completely dark patch of the sky that the Hubble detected just by staring for 10 days, something like 100 hours, is itself an entire galaxy.
Yeah, and in fact, the region that they chose to study was one that on the Palomar Sky Survey, the photographic sky survey, I think there were 3 objects in it. That was it.
Right.
It was empty, essentially, and then suddenly there were thousands of galaxies that appeared.
So this is also very relevant to your work because it must say something about dark matter and dark energy. I mean, if galaxies are forming so early, is that a suggestion that dark matter's playing
Yeah,
so dark matter is also
our
invisible
ideas
matter.
about cosmology really have evolved in the last couple of decades, and so we do appreciate now that there is dark matter in the universe, and there is this acceleration, and so the expansion that we measure today, the age that we infer, depends on the amount of dark matter or the amount of dark energy. We need to understand all of those things to determine the age.
John, the oldest galaxies in this image are about how old, do you think? Like the earliest thing that Hubble's seeing in this?
In that picture, I'm not sure which is the oldest one that we found, but Hubble has, for a long time, we could see within about 1 billion years of the Big Bang, and there's some claims that we could see about twice as far back, toward like within 500 million years of the Big Bang, and like one or two things we were very lucky to find. And now the Webb telescope, actually, we immediately find many, many, many.
So this was a big motivation for the Webb telescope, because it's saying, look, Hubble's looking back to maybe 1 billion years after the Big Bang, maybe 500 million, and there's a bunch of stuff there. It's not seeing the first light of galaxies and stars. And to do that, you need to, as you said, go into the infrared and go even earlier. To how early can James Webb Space Telescope see?
People are already claiming observations at a redshift of 15, which I'm not so good at my calculation of the time that it takes. But 15 is about twice as far as we could see before in that measurement. And so
I think that's like
very first
100
picture
million
we showed
years.
had one galaxy that sort of jumped out. It was 8.5 redshift and an age of 13.1 billion. So very, very close.
old.
And it was actually no problem at all to find it in the picture. It was just jumps out. So there are many, 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 many targets that we are going to study now.
Now, let's get to 2 weeks ago, just over 2 weeks ago, you revealed your own deep field image from the James Webb Space Telescope. Now, this is what Hubble saw in a similar patch of the sky. So it's still impressive. Hubble's seeing, some galaxies. Each one of those objects is itself an entire galaxy. But this is what James Webb reveals, its own deep sky image.
Whoa, yes. Yep.
But what's really fun, too, is you can look on the web, and they have now adjacent images, one from Hubble and one from James Webb, and you can use a slider to go across and actually see how it's improved in all of these new images. It's really impressive.
Just explain to us what we're really looking at here, because there's something very specific going on with the cluster of galaxies in the front.
Yeah, so this is the SMAX 0723, that one?
Yeah.
Yeah, so this is a cluster of galaxies that's not so very far away, and there's so much material in it. The gravity of that cluster of galaxies is bending the light from the more distant ones. So we see all kinds of funny shapes in here, things that are not little round galaxies. They're stretched out into arcs and weird shapes and bubbles, and that's because nature gave us an extra lens for the telescope. It's called a gravitational lens. And we have catalogs of hundreds and hundreds of gravitational lenses to use. And this was a good one just to start with, because we knew we'd see something. And then, they are.
So you have the kind of whitish in the center galaxy that's closer.
Yeah.
But what's really interesting is that there's stuff behind it much, much further away, from much, much earlier in the universe, and it's bending around this galaxy in the front, and so that's causing these arcs and things, right?
Yeah, that's what those little arcs.
They're like fake images of the other galaxies behind it.
Right. So some of them magnified 10 or even 100 times.
Which
That's
means
huge.
you're seeing them better than you would have if that big galaxy wasn't between us,
Yeah.
or that cluster of galaxies.
So.
Yeah. So how old are some of the galaxies in this image, do you think?
Well, I think the older ones that I know about are about 700 million after the expansion. But I think other people have found some that are much closer to the Big Bang.
Yeah.
So,
Amazing. So you're really looking at the very, very first galaxies.
So, anyway, every day there's 2 or 3 or 4 more papers being published in the preprint server because I found one even farther than you found. Very, very competitive these days.
Let's look at another one of the images.
But the data were made public right away, so many people in the community are jumping on this, including our group, looking at some of the nearer galaxies. It's impressive. So the enthusiasm in the community is speaking in the archive.
And there were papers coming out in 48 hours, 36 hours. So this is called another one of, this is from Hubble. This is Stephan's Quintet, although I believe only 4 of them are actually interacting. So there are 4 galaxies interacting. And this is the image released from James Webb. Can you tell us how it's different?
Yeah, the several things. One is the one on the left there has a sort of blotchy appearance, and that's because we're actually able to see it's made out of individual stars. We couldn't see that before. They're red stars. They're called asymptotic giant branch stars. This is what happens to a star when it gets old. It sort of expands and becomes a super giant, a red giant. And so there are a handful of them that you can actually see in this galaxy and just jump out. Another thing you see is
This
we have...
is a galaxy that really interests our group.
Yeah.
Say that again?
This is a galaxy that really interests our group.
How
This nearby
come?
galaxy, because of these asymptotic giant branch stars.
Oh, because
So
you use
we've
them to
developed a
figure out the
method
distance.
to measure distances using
they're
stars like that.
pretty
And that's
good.
a new technique
Yeah.
that you've developed.
Yeah.
So you had this technique where you were in this controversy many decades ago, which felt like it was kind of resolved, and now it's kind of back, and you're developing new techniques to determine distances. So the James Webb, you're actually using these galaxies to figure out how far away they are, and therefore figure out how fast the universe is expanding. And
Yeah,
harm
I mean, the
number.
controversy is different now because we were arguing about this quantity called the Hubble constant
Yeah.
that had values between 50 and 100 when this factor of 2 existed. Now we're learning from measurements of the Big Bang that the value is somewhere between 67 and 73. And now, so a new tension, as people are referring to it, has arisen. And so with James Webb, we're going to measure the distances to galaxies using many different techniques to the same galaxy and improve our measurements. But it has an interesting implication, which is that if the difference is real, and it could be real, we could be learning that there's something missing in our fundamental standard model.
We realized there was something missing. We called it dark matter. We don't know what it is. We realized there was something missing. We called it dark energy. We don't know what it is. You're saying we could realize that there's something else that's missing?
Correct.
And we don't know what it is? Now, just to give people a sense of scale, what everything anybody has ever seen, ever, or ever will see, makes up less than 5% of the universe. And the rest of it is in these forms that we don't know what they are. So John, you were talking us through this picture, and also I have this other one, which is the same Quintet, but it's used a different camera on the instrument,
Yeah,
on
this is the
satellite.
This is the mid-infrared camera. So it picks up longer wavelengths, like between 5 and 28 microns it can pick up. So it sees interstellar dust. It sees stars being born in new clouds. So that's where they light up. We can even pull out particular molecules and make a map of the particular molecules. There's something called polycyclic aromatic hydrocarbons, which actually is what you get a lot in diesel exhaust. Anyway, we see them in space, and they are telling us about the chemistry of interstellar material. So those, a lot of what you see here are places where stars are being born, and they're being prompted to be born because the galaxies are colliding. So it's a map of where stars are being born. And also the upper one there is got a different shape from the others because it's got a black hole in the middle.
It has a black hole in the middle.
Yeah, it does. We call it an active galactic nucleus because stuff is falling in. As it falls in, it gets very hot. Some of it comes spitting out again. And we can even measure the rate of motion of things orbiting around the black hole and coming out in jets. And we can measure the chemical composition. We have learned so much about those that we could never see before because they didn't have the right tool.
So I just want to clarify. We see colors that go from red, low energy, to blue, high energy. This is light that's outside of the range of what human beings can see. It's beyond the red. We call it infrared for that reason. So these are falsely colored so that we can see them, right? It's like the detection is made in a region that the eye can't perceive. And, but essentially, in that waveband, the telescope can see right through things that we can't see, in the same way that X-rays can see right through us that we can't see, and then we can look at an image of the X-ray. So basically, you use these two different cameras to get deeper into the galaxy, past different layers, and see deeper in. The idea that galaxies collide, that's pretty phenomenal. What does that suggest, that galaxies collide, that they interact? You think that's rare?
No. Well, they interact gravitationally, right? So the force of gravity is pulling them together, and the way we understand things now
So
is...
our galaxy has collided before?
Oh, yes. The things
How-
have fallen in. We actually see the fossil remnants now of smaller galaxies that fell into the Milky Way. And that's one of the really interesting discoveries in the last several years, is you can actually see streams of these galaxies that were tidally broken apart as they collided with the Milky Way.
And our future is to collide with Andromeda.
Yeah.
So it's interesting because most of the galaxies that we see appear to be receding from us, and Andromeda is one of a handful of galaxies that's actually coming towards
Falling
us.
towards us.
Yeah. So we've got, what, 1 billion years or something?
Yeah.
Yeah.
We don't have to worry.
Yeah. I think there's more to worry about, more recent, more impending than 1 billion years from now. Tell us about this spectacular image. So you released about 4 images, right? And so this being the third object that you looked at. Tell us about this.
Yeah, this is Carina. It's called the Carina Nebula. It's about 7,000 light years away. But it's beautiful, as you can see, and it's a special spot because this is where stars are being born as we speak. This shows on the top half lots of bright stars, and they've burnt a hole in the cloud that they were born in, and so you see that. You can even see sort of wispy blue stuff coming up as it melts off the surface and evaporates. In the ridge that you see, there are several hundred brand new stars being born, and we can now see them in the infrared light. And so we're going to go find out what are they, because clearly we'd like to know, are stars born with planets? We tend to take a personal interest in planets, so probably they're in there. So we're going to study them as much as we can. There are, and the whole cycle of birth and death of stars is in this picture.
And so we stepped from very far away and we're getting closer, right, into our own neighborhood. And then this is a composite image made with different cameras, is that right? So what's the advantage of looking at it in this other way?
Well, you can pull out the features that matter to you. So you're trying to make sense out of this thing. I need a tour guide to show me all the thing that's in here. I need somebody with the circles and the arrows and saying, that's this and that's that. There's just so much in here. It's just, anyway, it's just, to me, I'm just stuck with
For
being
us,
it's
there are
beautiful.
already arrows pointing at the Cepheids. We don't have to do anything. The arrows come with the image.
So you look at stars in these regions. Cepheids are young, Wendy?
But we do find Cepheids in regions where there is star formation.
So Cepheids are those variable stars that are very reliable indicators of how far away they are.
Right.
And so basically a lot of what James Webb is returning is going to be of interest to you.
Oh, yes. And particularly because infrared radiation goes right through the dust. These young stars are forming in regions where there's gas and dust. And that's one of the complications in using Cepheids, is you have to correct for the presence of dust.
This was taken by Hubble. It's the Ring Nebula, and for comparison, this was the image that James Webb revealed. Can you tell us about what's going on in this Ring Nebula?
Yeah,
this is also in our galaxy.
Yeah, this is a relatively nearby. It is a star that is at the end of its life, and it is spitting out it has episodes of spitting up. So it sends out shells of material, and they're not exactly spherical. Astronomers can calculate spheres. We can't actually calculate this. So that's one of the reasons it's so beautiful. We also got pictures at multiple wavelengths, and I think I can just barely see that the right-hand picture has the longer wavelength.
Yeah.
You can see that there are actually 2 stars in the middle, and you couldn't even see that before. The star that you can now see that you couldn't see before is hidden in its own dust cloud. So now we know that's the one that blew up,
Right.
or is in the process of blowing up.
So it's a 2-star system. One of them blew up, but they're still orbiting,
Yeah.
even though one of them died.
So this is not exactly what we think of as a supernova, where it is a catastrophic kind of explosion. This is more like what happens to small stars. They just, stuff comes out in shells.
So one of the things to point out about James Webb is that because it's a bigger telescope, and resolution goes as the diameter, so the bigger the telescope, the better your resolution. So it's at the same wavelength. it can be factors of 3 or more better resolution than Hubble, which is
it's really
really powerful.
Quite amazing. Somebody showed me that there is a little tiny detail in this ring nebula that was thought to be part of the nebula, but turns out to be a distant galaxy. And when they blew it up, they realized they were looking at this distant galaxy edge on. So it even in this image of a nearby nebula caught something very far away.
Yeah, and what was interesting was it was pointing right at the center, so there were people in the group who felt sure that it was radiating out from the center of the object, but it turned out to be a distant galaxy.
Turned out to be a distant galaxy. And then these were images, like you were saying, John, where people got really excited and they started to hone in on these galaxies. Hubble on the right, James Webb on the left, and you're seeing right through this galaxy to these sort of to the actual individuated stars. You're seeing right through the gas and the dust to the individuated stars. One other image I wanted to pull out was one that's been floating around where I was told that this presently holds the record for the earliest galaxy, youngest galaxy ever observed. So the further away it is, the more we're seeing it in the past. This was maybe 300 million years estimated, I don't know if that's accurate, after the Big Bang. What's so interesting about the way it looks to you, Wendy?
Well, I think, so what's interesting to me is there's actually a lot more detail even in this really distant object than the most distant objects that were found by Hubble. So there's already detail about the shape, which is irregular.
Yeah, it's so irregular. Did it surprise you, John, that it was so irregular?
Yeah, maybe I shouldn't be surprised, but it has a shape. It's not just a little speck. You built a big enough telescope to find out that it has a shape.
And so it's going to take some build. By now, that surely looks different where it is. We just can't collect the light from it yet.
Right. It's now much farther away, maybe 40 billion light years away by now. Of course,
well, the other interesting thing to point out is that I think there was 2 hours of integration on this deep field, right? But Hubble already has days and days of integration on the deep field. So this is just tip of the iceberg of what will come when large amounts of time are dedicated to this field.
And as we march a little bit closer, even though that was further, this is Jupiter as it usually looks to us, and this is Jupiter as James Webb saw it. And what's going on here? Are we seeing through the outer layers with the infrareds? We're seeing into the inner layers of the planet. It's as though we're able to penetrate right past what we usually...
And you can even see, I think I see in this picture, the faint ring around Jupiter.
You can see a ring. Yeah. So like Saturn, Jupiter has some rings.
Yeah. And I think, is this picture that shows Europa in the lower left? I think so. Because Europa is a special target for all of us because we're sending a NASA probe out there to see what's coming out. It's an ocean planet covered with ice, an ocean moon covered with ice, and there's water that comes spitting out from the cracks between the ice blocks. So we saw that with Hubble, and so now we're going to go visit and fly a probe through those plumes of water. And in the meantime, we're going to point the Webb over there and see what do we see about those water plumes.
And so there's a question about whether life could have arisen in the oceans of Europa, which makes it particularly interesting.
Yeah. So that brings us to one of the last topics, which was revealed in these past couple of weeks. This is a particular exoplanetary system, meaning it's planets around a star that's not our own, and it's in our own galaxy. TRAPPIST-1 is an interesting system that you will turn your attention to. As I understand, it has at least 7 planets. So we've seen some thousands of planets in our galaxy, but we believe there are how many? I mean, how many do you think in our galaxy?
Probably 100 billion. I mean, on average, one for every star. It's a huge number.
So possibly more planets than there are stars.
Possibly.
Yeah. And you made an announcement which didn't get as much chatter in general because it was harder to understand, I think, for people. So you did look at an exoplanet, not TRAPPIST yet, but you looked. Tell me about the planet that you looked at.
Yeah, it's a Saturn mass planet the size of Jupiter because it's orbiting so close to its star that it's a roaster. And so we observed it to demonstrate that we could do this. It's a technique called transit spectroscopy. So some of the starlight goes through the atmosphere of the planet on its way to the telescope, and you can analyze that and say, well, what are the molecules in that atmosphere? And so we showed that, as we knew there would be, there's water in that atmosphere. So we knew because we observed it before with Hubble. So this is just a proof of principle that we can do this work, and it worked better than we ever hoped.
That's phenomenal
Yeah.
that we're seeing water
Yeah.
on a distant planet. It is absolutely phenomenal. Now, why is that such an important biosignature?
Well, if you want to know about these little guys, these little TRAPPIST planets, those are about the size of Earth. And some of them are about the temperature of Earth. So are any of them like Earth? We'd like to know. So that's the sort of number one question for exoplanets. Do these little rocky planets that could be like Earth have an atmosphere? So that's number one. And if they do have an atmosphere, can you see water in the atmosphere? Do they have an ocean maybe? So that's possible, and we're going to try it.
Mm-hmm. And so, I mean, this technique that John was mentioning, it will be possible to look for signatures of water and carbon dioxide and other molecules besides water to see if they might be biosignatures. Because there could be water without life. Mm-hmm. But I think a combination of ground-based telescopes and JWST in the future.
So I believe it was one of your colleagues who said, methane on Earth is predominantly made by cows, but that doesn't mean if we see methane in another planet that there are cows. Right.
So it could be chemical signature also.
Right. So what are we going to need as a biosignature to decide, we see evidence of photosynthesis, we see evidence of something metabolizing the atmosphere. What would it take for us to be convinced that there were cows?
It might not be the cows, but...
So what we know we're going to try eventually is to get all the spectra that show the chemicals that are in an atmosphere of another planet. So ones that everybody thinks about, we'll start with oxygen, because here on Earth, oxygen is a product of life. We wouldn't have it much. But then, of course, astronomers are skeptical. We say, well, I bet I could think of another way. And so when we get to where we see that in some exoplanet, we're going to have a long story and a long argument. I think I can prove that's it, or I think I can't. I think you're wrong. So this same thing that Wendy had to go through with her measurement of the Hubble constant is going to be, it's actually worse, because it's not just a number. It's what does the number mean? And is there any other way to explain what you see? So I used to think one of these days we'll need Yankee Stadium to announce our scientific results. But it's actually harder than that.
So there's a big range that James Webb Space Telescope is doing, I think we've seen. We're looking at planets nearby, and we're looking at the most distant objects. That's really quite a stunning span. And so I was very interested that you released all of these images at once. I thought it was very smart. It gave people a sense of what's to come, and without leaving sort of these gaping holes. One topic I have to ask about, because it's my absolute favorite, before I open it up to questions, is about black holes. What will James Webb be able to tell us about black holes?
Well, I know the thing we started out asking was, when do they form? Because the big puzzle is almost every galaxy has a big fat black hole in the middle. Our Milky Way does. We got a picture of one in M87 just not long ago with millimeter wave observations. So they all have them. So how did that happen? We do not have a good story about how they could get there, and especially how they could get so big so quickly. So our hope is that we'll be able to see the first ones growing way back in the early universe. And they'll be able to say, either this came from the Big Bang itself, or they came from some new story that we haven't figured out yet, or they came by, anyway, there's a handful of different ways they could happen, but we don't know which ones are right. So that's the number one thing. Then closer up, you want to know, what are they doing to the galaxy that they're in? So we already have observations that show the molecules orbiting around the black hole in that picture we showed you before. So we're beginning to learn what are they doing to the galaxy, as well as how do they grow.
Now, Wendy, this isn't direct to your work, but are there ways of using black holes to make estimates of distances, maybe quasars?
People have talked about that. I think the difficulty with measuring distances. There's so many factors that can affect your measurements, astrophysical reasons why you could have large amounts of scatter. So I think there may be a way of using these in the very distant universe, but not for the kind of precision measurements that we're talking about now that would tell you something about whether there's missing physics in our standard model. But I wouldn't be surprised if with more data, people will come up with a technique that will let you measure distances over very long range in the universe, but just not to the accuracy that we're talking about tonight.
No, but how excited would you be just as a generalist to get more information about the black holes?
To get what from black?
To get more information about the black holes. I mean, just as a generalist.
I think what's so exciting and what we're seeing is we're going to learn something about pretty much every
Everything.
aspect of astronomy. So yeah, I think there's surprises in store for us, and those are going to be some of the most interesting observations, right? I think all of us know the kinds of things that Webb will do because we've been waiting for years to do them. But it's the serendipitous things that we can't even imagine now that I think are going to be probably the
Incredibly
most
exciting. So I know it's hot in here, and I love you all. Nobody's budged. You're amazing. You
Yeah,
could
it is
literally
amazing.
hear a glass drop, which happened like 2 or 3 times. I just wanted to throw this up before I open it up to questions. This was a piece that our founder at Pioneerix, Dustin Yellen, made for Quanta magazine for an article written by Natalie Walkover on the James Webb Space Telescope,
Yeah.
which later won the Pulitzer Prize. And next to Galileo, that's me. So, we're all in this together, is what that's to say. So with that as our backdrop, before I open it to questions, it's such a pleasure to see you both again and to talk to you both again. Please join me in thanking John and Wendy. We have a microphone. Come on up to the mic. I'm only going to take a few questions. You can actually tweet questions at me, and I will answer them and also throw them to the NASA Web group. And we'll maybe some other experts on the team will be willing to respond to questions for the next few days. We love doing that, so feel welcome to do that. Please, questions. Whoever's at the mic, feel welcome to get started.
Hi. First off, thank you. Could you speak to basically the successor to the James Webb Telescope? I know it's obviously early, but already what are people talking about of ways to improve the James Webb? Is the time horizon similar to we're looking 30 years out? Do we expect it to be 20 times over budget? Like all the anything into the process and hopes for the next telescope?
Yeah, we can say a few words. We know the National Academy of Sciences has a process every 10 years to tell us what they think we should do. And they said, please build us another telescope more powerful than the Webb that can be capable of seeing actual images of Earth orbiting a star like the Sun. And that's special because that's really hard, and that's most like home. So if you think you're going to see signs of life around another star, that's the way you have to do. So we're going to try. How long does it take? 20 or 30 years, probably. And is it going to be over budget? I don't think so.
I think people have learned their lesson.
We learned how to budget now.
Well,
Yeah.
it just means it's a good time to be alive right now.
It is, and in fairness to the budget for James Webb, the way the accounting is done now is different than it was at the time when Dan Golden said build this thing for $500 million, because it didn't include technology development, it didn't include the launch vehicle, so a lot of it was different. So I think what John says is right. There's a different way of doing accounting now, and a lot's been learned. So I don't think it will have the same. I hope it won't have the same kinds of issues.
And let's do a more accurate comparison. It's still less than the price of an aircraft carrier, right? So let's keep it in perspective. It's staggeringly expensive, but it's less than the price of a single aircraft carrier.
Yeah, so another bit of perspective. By the way, the worldwide budget for space stuff is about $490 billion a year. So just that's you could buy 49 Webb telescopes every year for that budget.
Well, the other
Please,
thing, I don't remember the exact number, but if you amortize over the 20-year mission of this telescope, it's I don't know, few cents per taxpayer
Right.
per week. It's not, in a relative sense, that big a price tag.
Yeah. Thank you so much for your question. Next, please. Yes.
Hi, question for all three of you. What single observation would you be most surprised by from the Webb?
I think if I'd be most surprised, I can't tell you then, because I don't know what it would be. I mean, you could ask what would be the single most exciting result. I don't know. What do you think, Wendy?
Of these new results that were just,
Or just over the lifetime of the Webb Space Telescope. What would blow your mind?
I think, again, it's the unknown that will blow my mind. It's something that we just can't anticipate now, that it'll be something we're not even imagining. But I think, anytime you have a jump in capability, so this telescope has greater wavelength capability, it's larger, so it's more sensitive, has higher resolution. We're going to learn a lot of things from this telescope, and I'm prepared to be excited by a lot of things. But I think, the planet stuff and the spectroscopy that this telescope is capable of, including for studies of galaxies, is going to blow the field wide open.
Yeah. Amazing. John?
Yeah, I think the places where we have the biggest surprises coming will be in the very early universe, because we've never seen it before at all. And those planets. Everything we know about planets is a surprise already. So why wouldn't we get some more surprises?
I think, to give a fair answer, I think that physicists are not as excited about knowing things as you would imagine. We really love being surprised. It really is the best. And if we discover that there's another contributor to the dark sector, I think that would be absolutely revelatory and would be really exciting. And I don't know, Wendy's going to be in the middle of that, I have a feeling. Next question, please.
Oh, hi. So, as you know, the Earth is heading towards total civilization collapse due to climate change. And that's going to mean, pretty much constant droughts and famine and floods and hurricanes, hunger, homelessness. And so I know that when Jeff Bezos took a little trip to space, that was the equivalent amount of CO2 that 1 million regular people would make in their whole lifetime. So my first question is, how much CO2 was emitted by this project? And also, at what point do we say that, well, the amount of CO2 emitted by space travel is just no longer ethical because of the cost of human extinction?
Well, there's an awful lot of questions in there. I would say a couple of things we've learned. One is that if you can define a problem that has a solution, you can solve it. We pulled together 20,000 people around the world to make the Webb telescope, and we made it work, and it worked beautifully. So if you want to try another hard problem, well, we tried another hard problem. So the things you mentioned are hard problems, but we could actually pull together to solve them if we felt like it. So why wouldn't we try that? So I'm remembering President Kennedy said we were going to go to the moon and do the other things too. He was not saying we're going to do this and that's the end. We were going to prove that we could do hard things, and we would learn how to do hard things, and that would be even more important than going to the moon. So he said it, and I still think it.
Mm-hmm. Absolutely.
Yeah, and I think to amplify on that, to build the James Webb and 20,000 people, John is telling us, and it involved international collaboration, it involved universities, it involved industry, it involved a really dedicated group of people who wanted to make something happen. And it is a phenomenal example of how you can solve difficult problems. It really is. And I think we've seen two of them. One is also the development of vaccines that occurred because of international cooperation. And climate change is something we have to deal with as a world, and I think when people want to do it, it happens. And we've got the know-how to make it happen.
Yeah, absolutely.
I want to add one other
Please,
thing, which
please.
is if you only read the newspaper, you don't know about the good news that is happening. And I subscribe to something called Future Crunch, and every week or two they send out a nice list of wonderful things that have happened and nobody notices. And so if you want to know, can we solve hard problems, then you should actually read something like that, because you know we do solve hard problems. And it's just, it won't make the news.
Absolutely. Thank you, John. Please, last question.
Oh, hello.
Sorry for the rest of you in the line. Last question.
Thank you, by the way. I'm curious if Webb is going to potentially shed any light on the question of dark matter. And it was brought up earlier, but I've read some articles recently. And I don't know, there's a question of whether or not dark matter and dark energy actually exists.
Whether or not dark energy actually exists.
And I'm curious if maybe the precision and specificity through which we can discern information from eons ago, that through Webb, that we might gain more insight.
Yeah, I mean,
into
sometimes
answering that question.
Sometimes we make mistakes, and dark energy is very, very difficult. Wendy, I think this is really in your ballpark.
Yeah, I think it's an important question, and I think if we start with dark matter, I mean, the idea that there might be dark matter actually was developed in the 1930s with the measurement by Fritz Zwicky of galaxies in the Coma cluster, and I think it was ignored for decades because people just didn't think that it made any sense. But with time, evidence accumulated that it wasn't just motions of galaxies and clusters, which indicated that they were moving faster than they would if there wasn't more matter there to bind them to the cluster. Same turned out to be true for stars that are orbiting within galaxies. They are rotating much faster than they would be if there wasn't more matter to hold them there. Then there was measurement of gravitational bending of light that was predicted by Einstein. We saw an example of that in the cluster. And then there was measurement of the microwave background. And so there are so many pieces of evidence now that are completely independent and based on completely different physical phenomena that it's very hard to imagine that there isn't something like dark matter there. We don't know what it is. We haven't measured it in a laboratory. There's a lot of work going on to try and understand the nature of dark matter, but there's something there that we just can't see, but we measure its effects because we can see what happens to the luminous matter in the presence of the dark matter. Now, dark energy hasn't been around for as long. The original evidence came from measurement of type 1a supernovae, which turned out to be fainter than you would expect if the universe hadn't been speeding up. So that was one piece of evidence. But then there was more evidence that came from measurements of the microwave background. You need dark energy to explain the fluctuations in the spectrum of oscillations from the Big Bang radiation. So you need dark energy.
Completely different.
Completely different. And so with time...
Unrelated.
Yeah, so it's a good question. And I think, most astronomers were extremely skeptical about dark matter for decades, but now the evidence is just proven to be overwhelming. And it's increasing for dark energy as more and more measurements, different kinds of measurements are being made. But you always have to keep asking because we don't know what the stuff is. We have no idea. It's a mystery.
Can I ask one more question really quick?
Very quickly.
Who has access to the telescope?
Oh, John. Who has access to the telescope? It's an important question as an international collaboration.
Yeah, actually, anybody in the world can send us a proposal. And we received proposals from, I think, 1,100 different groups, including 4,000 scientists spread around almost all countries. There are a few countries that didn't have anybody in the middle of Africa, but almost all countries have participants. And it's done by a process we call dual anonymous, which means when we read your proposal, we do not know who you are. You can be a cat, and we would not know. So, and we try to find the proposals that are the best. And then we publish the data. Some people get to keep the data for a year, and some people give it out right away. So that we're benefiting now from the ones that are coming out right away.
Yeah, our group gets time in November, so I'm really excited about that.
I know that we've run out of time, and this was just phenomenal that you both agreed to come. It was absolutely phenomenal for you to be here. I do want to say that if a tiny fraction of the ingenuity, creativity, and just sheer will and international collaboration, as you were saying. A tiny fraction of that was, as you said, thrown at other problems. If we could get past those obstacles to care that much about the solution as people cared about the James Webb, watching people with the little lights and all the detail, and every single person caring to that extent, we could tackle any one of these problems, there's no question. So thank you so much for the inspiration, and thank you so much for being here.